Good to be with you all. Thanks for those of you on the line for sticking around for the whole session today. And for those of us in the room, let me move to the next slide. Oops. So I'm going to cover basically three parts in this talk. First is to give a little overview of a life cycle assessment for those of you not familiar with the concept. And that also I'll include the comparisons that we made for the lamps. I will then discuss the results of our comparison, which I have to emphasize are preliminary at this stage because we're using a slightly out of date LCA database, and we're in the process of updating that now to the most current version of SEMA Pro. And then finally, I have some next steps and an invitation to anyone in the room or on the call who would like to be a peer review person, because that is part of the LCA process that we publish or sort of have a peer review before publishing the final report. So I need volunteers. Okay, so the LCA. So this is an international standards organization, ISO 14000 process. It's a recognized way of quantifying the environmental and sustainability impacts of products over their entire life cycle. So we use the phrase from cradle to grave. And it spans the raw materials, we're talking about going from raw materials extraction to making parts, assembling those parts into products, transporting those products to point of sale, then being installed and used in the home and then, or business, and then disposed of. So at every stage of the process. And you can see that here in this diagram, we really sort of break the LCA into 5 chunks: the raw material extraction, manufacturing, transport, use, and end of life. So that's the an illustration of it. And so this comparison, we wanted to understand if you have an existing fixture in your building or your home where you're using a fluorescent tube, is it environmentally sustainable to upgrade to an LED tube in that installation? So not changing the fixture at all, keeping the same ballast and driver, just changing the light bulb from a fluorescent to an LED retrofit. These are LED retrofit tubes that are designed to operate on the fluorescent ballast in the same fixture. So that was our key question. And we had 2 comparisons. One of them was looking at in the US, we call this a T8. In Europe, I see TLD used quite a bit, but essentially a 1-inch diameter tube of 60 centimeters in length. And in the baseline, we were using an 18-watt fluorescent lamp, cool white, rated for 20,000 hours and 1,350 lumens. And there are 2 retrofit options there for that product. One is designed to operate on a high frequency ballast, if you have that. The other is on a magnetic ballast or a low frequency ballast. And they're both rated at 8 watts. They're both cool white and both rated for 60,000 hours. So triple the lifetime. And the light output is a little bit lower, but you need to bear in mind that these bulbs are designed, and you can actually rotate them when you put them in. So the light is directional as it comes out of the LED. So the fixture losses are actually lower when you put one of these tubes in. So even though the lumen output is less, the equivalent illuminance in the room, the illuminance in the room is equivalent. And then on the T5 side, we looked at a 35-watt cool white. This is a 145 centimeter lamp. It's rated for 24,000 hours, so slightly longer than the T8, 3,300 lumens. It's a high output lamp. And then 2 retrofit options. Again, there, both of these are for high frequency ballast because that's all T5 has. One was an 20-watt cool white, 60,000 hours, and the other is an 18-watt cool white rated for 50,000, slightly less expensive product. And we use a slightly lower fixture efficiency there because the T5 tube is a smaller diameter. It's 5/8 of an inch, so there's less self-absorption of the light in the fixture. Oops. Okay, so here's a picture of the fun stuff, just to show you the teardowns. We actually did I call it a reverse engineering analysis. We disassembled each of the 4 LED lamps. We measured, we weighed, we recorded, and we noted part numbers wherever possible. So these are some of the photos that we took as we disassembled, and we created an Excel spreadsheet with a parts inventory. And just one of the photos here, just for fun, you can see on that circuit board, this little black chip. It's a constant current power supply. You can read the number on the chip, 9938D FAC 51X. And then there's the word link. If you click on that link, you can find that product for sale. So we were able to verify a lot of the parts. And then from those specifications, you can get a little bit more information about them as well. So we went down into the weeds on these LED tubes. On the fluorescent side of things, due to the mercury content and health and safety aspects, we decided not to disassemble these. So the T5 and the T8, which you see here, we measured them, we weighed them, we recorded as much as we could about them. But then we relied on existing published LCA literature about fluorescent tubes, some going back to 2009, 2011, there's a few papers, and we cited those and we scaled the component parts of the fluorescent tubes because they haven't changed that much basically in the last 10 years. We scaled those parts to get the equivalent of the fluorescent tubes and avoid the exposure to the mercury. So here's the inventories of the lamps. This is just two examples. We have one of these tables for each of the lamps. So all six, 3 T8s, 3 T5s. And can you actually read that? Yeah, it's kind of small, but this is the Excel spreadsheet. We also included, just to mention, the packaging, an estimate of the production, energy consumption, both gas if you're melting and fixing glass, and also electricity, obviously, the transportation involved, the energy and use, and that really matters in terms of the rated lifetime, and then the end of life, assuming estimates of what is recycled and what is not. So for end of life recycling, we assume 30% of the fluorescent tubes are recovered at end of life, and about 70% are disposed of improperly. And we used a 50% estimate of recycling on the packaging, so the paper and so on. And then I guess I say here that for scaling, the lamp's total light service output is calculated. So for the T8, this is just one example. The T8 fluorescent, as I mentioned, was 20,000 hour lamp, and I think it was 1,350 lumens. So over its lifetime, it will produce 21.6 mega lumen hours from that lamp over its lifetime. And for the LED, which was rated 60,000 hours and it was 1,000 lumens, it will produce 60 mega lumens, excuse me, 60 mega lumens of megalumen hours of light. So about 3 times as much lighting service from that product. And then I just mentioned here that the software needs to be updated, as I said earlier. But you can see, for example, on the fluorescent lamp, we have argon gas, krypton gas, mercury, noble earths. We have the phosphor, we have aluminum, glass tube, et cetera, et cetera. So there's a lot of parts. And then these are the components: paper, packaging, manufacturing, distribution, both sea and air. So we're assuming manufacturing is taking place in China and it's being sold in Europe, energy and use, and then end of life. So these are the categories you see here. And then you see a much larger parts inventory on the LED because you have circuit boards on both of those. Okay. So let's get to some of the results. So I want to start by talking about the environmental indicators considered. So there's 15 indicators. We looked at global warming potential here is an important one for the governments in the SSLC platform. We also looked at ecosystem damage, human toxicity potential, hazardous waste, land use, ozone depleting potential, radioactive waste, and so on. And in fact, in the software for LCA, there's over 100 of these indicators. And so as an analyst, you choose the ones that are most important from your perspective and report those. But there really is a wealth of data for people who are interested in working in this field. Okay, so, and this is a snapshot just comparing 2 of the lamps, the T8 fluorescent baseline and the T8 LED lamp, just the first one, which was the high frequency ballast. And you see the yellow shaded, and sorry, there are 5 categories of impact. So there's raw materials, which is the little green section. There's manufacturing, which is the black. Transportation, which you can't even see. Energy and use, which is yellow. And then disposal, which is the blue. So you see from an impact point of view, and there's percentages over here on the right, where I just took the simple average of all 15, all 15 indicators. I just took a simple average of them. So there's no weighting here. But you see that essentially 97% of the impact of the fluorescent lamp is from the energy in use. So there's very little material in it, right? It's just glass, some phosphor, and a bit of metal. So there's not much to it. But energy in use is the most important impact. And when you compare that to the LED, you see that the energy in use is about 90%. There's a lot more raw material that goes into the LED retrofit. So that impact of those parts and so on in the assembly in the manufacturing has been more impact. So the energy in use is still the dominant factor in LED, but it's actually coming down a little bit. And that's an important point because I come to a sensitivity analysis in the closing. And now I want to introduce something called spider plots, which are really fun. So it is a circular, it looks like a spider's web. And we've clustered these 15 indicators into indicators of air, water, soil, and resources. So those 4 categories. And essentially on this spider plot, which you'll see in just a second, the product with the largest impact is on the outside perimeter. And as you move in towards the center for that indicator, that is less impact. So the center, you have the least amount of impact. And so this is the T8 comparison. So the blue line on the outside of this is the maximum impact, and that's the fluorescent baseline. That's the T8 fluorescent. And then you look at the T5 high frequency and the T8 high frequency and the T8 electromagnetic. And you see they both have come in about half the distance from the outside of the circle to the center. So, essentially, when you average those 15 impacts together, the LED is between 48 and 52% of the impact of the fluorescent. So essentially, you can say here the answer to the original question is, basically the environmental impact is reduced about 50% by switching to an LED retrofit lamp in your existing fixture. That's the crux of it. And that's for the T8. And if you go to a T5, T5s are more efficient. They have less material in them, right? They're smaller diameter, less phosphor. And they also have longer life. So the LED retrofit here is not as good as it is for the T8 scenario. We're looking at 61 to 63% of the impact. So we're saving about 40% of environmental impact, but it's still better on all 15 indicators. So that's a nice finding. So just to go back for 1 second. So 50% savings roughly on the T8 and approximately 40% savings on the T5. Okay, last slide. So the conclusion is that upgrading with LED retrofit lamps does have a net environmental benefit. As I mentioned just now, 50% for the T8s and about 40% for T5s. But then my question was, because I'm discussing this with a university in the Midlands here in the UK, well, I may not leave these LED tubes in the ceiling for 60,000 hours. We may upgrade that building before then. At what point do I cross over the threshold of being more environmentally sustainable? In other words, how long do I have to leave it in the ceiling to have less impact than if I just left the fluorescent there and then changed the fixture in 3 or 4 years' time? So I did a sensitivity analysis just to see what that was. And essentially with the T8 lamp, you need about 6,000 hours of use before you cross that threshold. So as long as you're going to use that fixture for another 6,000 hours, say, for example, a typical building might be 4,000 hours a year, so maybe a year and a half. you would then be net benefit. You'd have a net benefit on the environment of switching to LED right away. For the T5, it's a little bit longer. You need about 7,000 hours. So pushing more 2 years for that. So if you're not going to change the fixtures within the next 2 years, definitely pop in an LED retrofit lamp. You will then have a net benefit overall from an environmental perspective. And of course, if it's going to be longer than that, if you're talking 3, 4, 5 years, and it absolutely makes sense. As I mentioned, energy is still the dominant factor for both the baseline, the fluorescent lamp. It was 97 to 98% of the impact compared to the LED, which was around 90 to 92. And then I just have a cautionary note that these are preliminary and indicative findings only. We do need to update to the more recent LCA software. We were urgently trying to get it for today. I feel a bit like Steve with his lamp testing. It's like, oh God, next week. But yeah, that's what's happened to us as well. We weren't able to get the SEMA Pro version 9.5 working properly. So these are the results based on an earlier database, but they are very much indicative of what we'll find. So we felt it was still safe to say that. And then finally, a request that we do need a peer review team. So if anybody on the call or in the room is interested, the email address is here for the annex. If you could just write and let us know, we would love to send you the draft analysis when we have it ready, and the report will be published later this summer. And that is the final slide. Just to say thanks to George Zisis from University of Toulouse and his PhD student, Rita, for their help with this process. It's a collaboration between us and that department. Thank you.
Thank you, Mike. Very interesting. We really look forward to when you have the updated database with the most recent. I guess the results are to improve even more, but we'll see.
Yeah, it's just that it's based on an electricity power mix that's 5, 6 years old. It's not going to be as accurate as today. Yeah, that's that type of thing.
That's correct.
Yeah. So.
Okay. Any questions from the floor?
Sean, do we have any questions in the chat? Okay, great. Oh. Okay, I can do that here. Yep. Okay. So California. Okay, that's the California question. Okay. Yeah, thanks, Sophie. We'll take that online. Great. Were the impacts normalized to the functional unit, i.e. the lumen of output and lifetime? Yes, it was. Thank you for the question. We did follow that. The functional unit being the mega lumen hour of lighting service, and then also taking into account fixture efficiency. So for a fluorescent lamp, in that fixture, light is going in all 360 degrees up into the luminaire and reflected back out again. So there's some absorption on the surface, and there's self-absorption back into the tube. So the total lumen output of the fluorescent lamp is, we use 80% for the T8 and 85% for the T5. And for the LED, we allowed it to be 100% because it's all coming down at basically between 160, 170 degrees out of the fixture. So if you have any suggestions on how to improve those numbers, we're all ears, but that's what we've used for this first analysis. When fitting the LED replacement tubes in luminaires originally designed as fluorescent luminaires, do you see a problem with the original product design liability? Who is responsible for this functional product change or modification if something goes wrong? Yeah, so it depends on the jurisdiction where this happens. So I know, for example, in the United States, because this question came up in the state of California, that there's a sticker that the electricians put onto the fixture after making the change. Sorry, I'm thinking of ballast bypass, actually. So I think for your question, if it's an LED tube that is operating on fluorescent gear, it would be the LED tube manufacturer who would carry the warranty on that product. I can't say that they would also take liability for the fixture. I don't think so. But if the ballast is functioning normally, that's what these products are designed to do for retrofits. So they should carry, they carry a warranty on the LED retrofit tubes, but probably does not extend to the operating environment, like the ballast that it's operating on. I don't know, Steve, do you want to add anything to that? Do you have any other thoughts on that? Okay. I don't know, Sophie, if I've answered your question. You have my email address if you want to send a follow-up, and I'd be very happy to have you as a reviewer to make us work hard to get this right. Other questions? Any questions in the room?
Okay.
Super.
Brilliant.
Okay. Over to you, Nils.
Thank you very much. George was supposed to do the roundup here, but he's actually, I think, oh, there is a question. Yeah. Yes. No, they cannot, okay, they cannot move it this far. Thank you, Steve. Yes. So, yeah, brilliant. I thought you were pointing at mine. So that's okay. Thank you. I'll start over. Anyway, George was supposed to be here, but I think he's electing a fellow professor in Toulouse or something like that out there. So he had to move out for internal university politics, I think, or duties, I should say. It's more. Anyway, thanks for joining us online and for joining us here on site. We, as you know, we do webinars every now and then, and we will be continuing with that. We'll also try to do events wherever we are, but by nature, since we meet in a country roughly every 3.5 years or so, there won't be frequent seminars in a given country. But it's great to be able to share this with you. It's great to have your input, and I hope you all can help pick up on the various reviews we do sometimes, like this review for the LCA. When we do our performance requirements, we also always do a very large public review, and that comes back on other things. So it's really important to extend to this larger community. We are really excited to be entering our fourth term for 5 years, looking more into, let's say, systems integration and controls, and the more complex nature, which are true challenges. How do we really test luminaires for a number of issues? It's, it gets more and more complex, harder and harder to make the system boundaries, but it's also a nice challenge, and I think a very good challenge to be sharing with the right kind of people, which I think I have the benefit of working with. So thanks a lot for joining us, and I won't keep you anymore. Some of you, I guess, stayed up very late wherever you are in the world, and some of you went up very early to join us. That's also commendable. So thanks, keep up and try to keep awake. And a few of you, you're well-deserved good night. Okay, for those of you who are here on site, there are some drinks outside here, outside the door, and the rest of you take care. We'll be meeting again somewhere physically or in space. Cheers.